My name is Adithya, and today I'll present my comparative analysis of smartphone speaker performance using digital sampling techniques. The work was conducted from June 10th to July 15th. So we'll start with our experiment. So, smartphone speakers design balances physical constraints with acoustic performance. My experiment quantified these trade-offs across three flagship devices: the iPhone 12, the Samsung Galaxy S21, and the Google Pixel 6, using a LabJack DAC system. Understanding these responses aids in applications from voice interface design to multimedia optimization. That's my introduction motivation. So the approach we used. So these are all the equipment we used: the LabJacks, the condenser microphone, and we validated our methodology through rigorous calibration. First, we characterized the reference signal path using direct DAC connections, achieving a sub 2% amplitude variance across the frequencies. For speaker tests, we controlled for room acoustics by testing in a damped environment with a fixed 10 centimeter microphone spacing. Each device underwent swept sign testing from 100 hertz to 10,000 hertz at maximum undistorted volume. So the results for the frequency responses. So as we can see in the Samsung curve right here, which is the dark blue, the Samsung has the flattest response, just plus minus 1.5 decibels from 1.5 to 4 kilohertz, confirms its balanced tuning. Meanwhile, when we go to the iPhone's plus 3 decibel boost at 2 kilohertz aligns with our independent test, showing its peak response precisely at 1980 hertz, optimal for voice reproduction but less ideal for music. So now if we look at the Pixel's 15.1 decibel drop at 200 hertz correlates with a smaller speaker enclosure dimensions. So So now we go for the quantitative analysis. At 200 hertz, the Samsung's minus 8.2 decibel loss outperforms the iPhone's minus 12.4 decibel, a 4.2 decibel advantage, equivalent to doubling the perceived loudness, while the Pixel's minus 15.1 decibel confirms that it has sub-bass deficiency. So when we highlight the 5 kilohertz one, the high frequency performance shows similar trends. Samsung maintains a minus 2.1 decibel at 5 kilohertz versus iPhone's minus 5.3, suggesting a better tweeter design. The iPhone also has the most colored response at the mid-range. So here, now let's look at our time domain analysis. So the time domain data reveals why the iPhone's harmonic distortion, visible as a waveform asymmetry, explains the colored sound. The asymmetry here. The Samsung's cleaner sine waves correlate with its neutral frequency response. The Pixel's clipping at above 85 decibels SPO indicates amplifier limitations consistent with a smaller power supply. So you can see the clipping here, Well, this is smoother. Well, these two are more smoother. You can see the clipping here. 1 kilohertz sine wave reproduction. So conclusions. So here, let's look at our engineering implications. The three key findings. First, speaker size directly impacts low frequency extension. The Samsung's larger enclosure produced 58% more power at 200 hertz than the Pixel. Second, our our environmental controls proved critical. Initial room tests showed plus or minus 3 decibel variations versus zero point 0.5 decibels in control conditions. Ultimately, these measurements explain why Samsung leads in audio reviews, while Apple prioritizes voice clarity, a perfect case study in design trade-offs, while Pixel tries to like balance their economics and makes their sound system a little bit worse. So here's the MATLAB code for the graphs. And so for the prior two, here's the table containing the waveform identifications between sine waves and all here, peak principal frequency, and any other peak frequency. So the one thing I wanted was the table here for question 6, which is the Nyquist frequency. It shows how to get all the waves. You need the Nyquist frequency to be twice. You need a sampling frequency to be twice the actual Nyquist frequency. So it's here. So to get a third of 10,000, we needed the Nyquist frequency to be 20,000. That's what we're getting here. And here's my lab notebook. So acknowledgements. Thank you for the TA team for equipment support. Thank you, Professor Steinberg, for clarifying my questions. And here's my references. Thank you.